Hello, everyone. I'm Yuan Gao. Today, I'll be presenting ProbMed, a probabilistic framework for medical multimodal binding, which we introduced in our paper. So, the motivation behind this project is that medical decision making inherently relies on many data types, imaging, signals, and clinical text. But existing medical vision language models typically treat modality alignment in a deterministic manner and focus mainly on image text pairs, for example, chest x ray and radiology report. These methods struggle with two challenges. There exists many to many correspondence between modality and narratives, i.e., one image might correspond to multiple valid textual descriptions, or multiple modalities might correspond to each other for prognosis. Multimodal integration beyond just image and text is a true clinical application, as in the real clinical setting. We bring together signals like ECG, echo, chest x ray together with existing modalities. Our core idea is to both learn this less deterministic and more probabilistic learning through probabilistic embeddings, i.e., distributions, not point vectors for each modality, and bind them across modalities in a shared latent space. This allows us to represent uncertainty, overlaps, and ambiguity in the alignment. Here is an overview of our model. You can see the block diagram on the right-hand side. We support four modalities: chest X-ray, or CXR for short, electrocardiogram, ECG, echocardiograms, echo, and clinical text. Each modality is encoded via a modality-specific encoder, producing parameters mu and sigma of a Gaussian embedding with diagonal covariance. A key aspect is that we assume diagonal covariance similar to previous literature in probabilistic contrastive learning, as it allows us to use this closed form solution for various probabilistic distances when calculating similarities between two latent representations. Looking at this in more detail, we enforce alignment across modalities via probabilistic contrastive learning, where each positive pair is paired viewed as a distribution and similarities are measured via Hallier distance. We also introduce a synthetic instance sampling loss, or SIS loss, within each modality. This samples multiple latent representations from the learned distribution and encourages the sampled points to remain consistent, i.e., reinforcing intra-modality structures. To prevent variance collapse, we also include a information bottleneck, or VIB loss. So this is the KL divergence to a prior. To train all of these modalities pairs at each iteration, we randomly pick one available modality pair, i.e., a CXR text, ECG text, or a CXR ECG or echo text to compute the contrastive loss. Plus, we always include the CIS and VIB loss. From here, we have a unified joint probabilistic embedding space with all four modalities living in it. We evaluated ProbMed across 13 medical datasets spanning CXR, ECG, and echo modalities, covering tasks such as cross-modal retrieval, zero-shot and few-shot classification, multimodal prognostication, and classification. And you can check out most of these results compared to common benchmarks in our paper, and the GitHub is attached below in the QR code. The part that I really wanted to highlight was the things that we can do with probabilistic learning. Now let's take a closer look at what probabilistic embeddings actually enable. In this figure, each point represents a latent sample drawn from our learned Gaussian embedding for a given modality. Notice how instead of assigning each image or ECG or any sort of modality as a single deterministic vector, ProbMed learns a distribution. This allows us to draw multiple possible representations, effectively creating synthetic samples in embedding space. When we apply this resampling in few-shot settings, say when we only have 5 labeled examples per class, we can expand these examples into dozens of diverse yet semantically consistent latent samples. And this is shown very well here, where we see that the performance improves when we sample compared to just using the mean. Additionally, in the zero-shot scenario, we can actually use the variance that is produced from these distributions as a way of filtering for prompts. So consistent with previous research in probabilistic contrastive learning, we see that we can filter these prompts in zero-shot using the uncertainty, and an improvement in zero-shot occurs.